Good morning, good day, good afternoon, good evening, wherever you are. It is my great pleasure to introduce Dr. Bill Daly, our keynote speaker today. Bill joined NVIDIA in January of 2009 as a chief scientist after spending 12 years at the Stanford University, where he was the chairman of the computer science department. Bill and his team at Stanford developed the system architecture, network architecture, signaling, routing, and synchronization technologies that we have found in most large parallel computers today. Previously, Bill was at MIT, where he and his team developed the J machine and the M machine, experimental parallel computer systems that pioneered the separation of mechanisms from programming models and demonstrated very low overhead synchronization and communication mechanisms. Before that, from 1983 to 1986, Bill was at Caltech, where he designed the MOSIM simulation engine and the Torus routing chip, which pioneered the wormhole routing and the virtual channel flow control. He's a member of the National Academy of Engineering, a fellow of the American Academy of Art and Sciences, a fellow of IEEE and ACM, and he has received the ACM Eckhart Macaulay Award, the IEEE Seymour Cray Award, the ACM Maurice Wilkes Award. He has published over 250 papers, holds over 120 issued patents, and he's the author of 4 textbooks. Bringing it closer to home, Bill is a pioneer of the NOC paradigm for modern SoC design. His paper, Route Packets Not Wires, is one of the most impactful papers in the field, showing close to 5,000 citations to date. It has influenced many researchers in the field, and it certainly influenced mine. In the intervening 21 years since Route Packets Not Wires paper was published in DAC, NOCs have become ubiquitous. They are used in GPUs, CPUs, and all kinds of specialized accelerators, largely replacing buses as the communication backbone of digital systems. Without further ado, let's welcome Bill as our keynote speaker today.
Well, thank you, Rado. I'm honored to be here. It's been a lot of fun playing with NOCS over the last 21 years. And so when I was invited to give this talk, I thought it was a great opportunity to go back and look at what is the same and what has changed. So let me start with, one of the things that's changed is, 21 years ago, NOCS were a new idea. Today, NOCS are everywhere. This is our Hopper H100 GPU. It's a petaflop of TensorFloat 32 performance. Depending on whether you're dense or sparse, 1 or 2 petaflops of FP16 and 2 or 4 petaflops of FP8. Enormous amount of computing performance, and that's done by a very large number of what we call streaming multiprocessors, SMs, that are all connected together. The SMs are these little orange things here by a on-chip NOC. This is sort of our view of what this will be like in the future when we have configurable custom blocks in there as well. We've been making these GPUs with on-chip networks for ages. Most recently, though, we've started doing it with CPUs as well. This is our Grace CPU chip. It's 72 ARM Neoverse cores. They're among the most powerful, out-of-order, single-threaded performance cores that you can get. And what's connecting them all together is a mesh network that we call the Scalable Coherence Fabric, because the messages it carries carry out the cache coherence protocol among these cores. They're all in one big coherent memory space. And then there's accelerators. This is actually an interesting example of a hybrid NOC-POC, network on chip, network on package, NOC-NOP. This is our Simba AI accelerator that we did as a research project in NV Research, where we have an array of PEs and a mesh network on die, and then they're connected up in a mesh network on package to build an even larger AI accelerator. A number of years ago with my graduate student, Atish Tarakia, who's now on the faculty at UC Santa Cruz, we built this Darwin accelerator for genomics. And a key part of it was a on-chip network to do the seeding calculation, where you basically are keeping score for various prefixes of possible alignments of how many of them match. And to do this, you have to do a lookup in a very large table in DRAM, and then using the index of that, go to a bin that's kept in a hash table. And we do this over an on-chip network. And one thing that's important is we're not just doing loads and stores over this network. If we did, we would completely overload the network. Instead, we actually send a a packet to the memory bank that would hold the bin. It's a hash table, so it has to walk the hash table, compute the hash of our tag. If they match, you go ahead and update the bin. If they don't, you keep walking with the open coding until you find it, and you update the bin. Then you have to check against limits, and depending on whether you exceed a certain limit, you can send a candidate to the output. In any case, anytime you are non-zero in the bin, the first time you increment off 0, you have to record that. So for the next go around, you can zero that bin out. But the on-chip network is key for all sorts of accelerators. Now, when you look at how they're used, you sort of find out what's important. And what's really important is energy. It's important for all classes of the use of NOCs. The GPUs and accelerators tend to have lots of parallelism, so they can hide the latency of the NOC, although you don't want to go overboard with latency because you then waste a lot of parallelism hiding that latency, and eventually you do run out. But in all of these cases, most of the energy is, or I should say much of the energy is in communication. When you have local computations, the operations actually consume a fair amount of energy as well. And particularly for the CPU case, the latency of remote operations is critical, and most of that latency is in communication. I remember having huge debates with people where they say, I don't know, the latency is in the memory, but if you look at memory, accessing the bit cell is really fast. All of the latency of memory is in the communication, is in building that network. And so what you really need to optimize for a NOC is energy and latency. Notice that I didn't put bandwidth down here, and that's because bandwidth is easy. We can make these channels as wide as we want. In fact, if you look at a lot of the things we do for off-chip networks, even that on-package network, a lot of hoops we jump through is because we have a limited number of pins. We don't have a limited number of pins with these NOCs. We've got lots of on-chip wires. They're very cheap. So let me go back and look at a little bit of the history. In some ways, in my mind at least, I started thinking about NOCs with this paper that was at DAC in 2001 that Radu mentioned, route packets, not wires. And in this paper, we sort of went through a mental exercise of, how you would build one of these on-chip networks, where we had a bunch of tiles with 3 millimeters on a side, which by today's standard is a very large tile. And we would, in each of these tiles, have a bunch of logic for the NOC. Now, one thing we've learned since this paper is you don't want to put the east output actually on the east side of the tile. You want to collect all the east-west stuff and put it on one side, east or west. But you want to have the routing logic here next to the routing logic here, so you don't have to have a long wire between them. Similarly, the south you would collect and put on the same side of the tile as the north. The other thing is this showed a torus, because I have been very, very much in love with tori since I did the original torus routing chip back at Caltech in 1985. But it turns out that a torus is just a really bad idea for a NOC. And the reason is, if there are routes here that should be easy and become hard. So for example, if I want to go from number 1 to number 2 here, there's no direct channel from number 1 to number 2. So it should be a 3 millimeter route. Instead, winds up being a 9 millimeter route. It's kind of like driving in Boston where you can't get there from here. I have to go first to 0 and then to 2. I can't go directly 1 to 2. And that's wasteful. I've increased the latency and the energy of that communication by a factor of 3 over what it should have been. Now, at the very first NOCS conference back in 2007, I gave a keynote, and I pulled up the abstract just to say what I thought was right and what I think is still right, and then what I thought was right then and I think is wrong. So what I said then is optimized circuits can reduce power by an order of magnitude. I still think that's right. It may not be quite an order of magnitude, but you can get a lot of energy efficiency by optimizing your circuits. Sending a 1 or a 0 across a chip by signaling with the power supply or ground is actually a pretty inefficient way of doing it. And then I said optimized topology can give an additional factor of 2 or 3 in area and power efficiency. And I'm going to withdraw that one. That's why it's underlined in red, because it's just really hard to beat a mesh. A mesh is going to route your packets in the minimum possible distance. And that's going to be essentially optimum for power efficiency and for latency. And what I think a lot of people have done over the years is try to use fancier topologies to bypass routers, so that if you're going a long distance, whether it's using express channels or a flattened butterfly, you can go across many tiles without having to visit an intermediate router along the way. That presumes that visiting those intermediate routers is expensive. And what I'm going to argue and give an example of in the remainder of this talk is it's possible to build these intermediate routers so that they're essentially free. Now, they're not going to be very, very smart routers, but they don't need to be very smart. So here's a recipe, and it's good to sort of walk through an example network design to illustrate some of these points. Of course, any design starts with requirements. So I'm going to take the example here being driven by a multi-core CPU system on chip, much like our Grace chip, say 72 ARM cores. Latency and energy are critical. The type of packets we're sending around are read and write, request and reply packets, plus protocol packets. A protocol packet is, for example, an invalidate, where it's much like a read request. It's an address and the command, the address and invalidate. And then for the read replies and the write requests, we are sending along 64-byte cache lines. And coming out of the CPU, these packets are in parallel. The CPU doesn't introduce any serialization latency, and we prefer that the network not introduce any either. Wires are very cheap. We can send this whole packet, all 512 bits of it in parallel. So the first element of I like to think of networks in terms of topology, routing, and flow control. The first element is topology. And it's really hard to beat a 2D mesh, because the 2D mesh will always give you the minimum Manhattan distance from one point to another. So this 2D torus that we put in our original paper was wrong. I do point out that in the original paper, we did talk about a mesh. And but basically what we said is, from these expressions, if wire transmission power dominates per hop power, the mesh is more power efficient. That's exactly true, and it does. The wire transmission power and latency completely dominates, and that's why you want to use the mesh and not the torus or something fancier. A little bit later in 2006, with my graduate student at the time, James Balfour, we looked at a bunch of design trade-offs for building tiled NOCS. And we talked about meshes and tori and concentrated meshes where you have many nodes sharing one node of the mesh, fat trees and other varieties of trees. The conclusions then don't really hold as much today, again, because the costs have changed. But even then, it was clear that one of the meshes wound up looking as a really good thing to do. Now, my one suggestion for improvement on top of the mesh is that if we could have diagonals, it would help. I suggested this to some of our technology people, and they gave me this horrible look. But in fact, there's no reason why we can't run wires diagonally on a chip. When I first started designing chips in the early 1980s, there was a huge debate between people who advocated Manhattan geometry for chips, everything aligned X, Y, and Boston geometry, where we would do transistors by making arcs, because of course that was the most efficient way, was to make the gate a circle, because then you would have the minimum area of the drain in the middle of the circle, and hence minimum capacitance on that node. Now, I'm not suggesting to go so far as to go back to making your transistors circular and the like, but having two layers of your chip where you can run the wires diagonally would be a really good thing to do. And the gain here is big. It's a 30% reduction in distance, right? If I need to go from this, call it node 0, 0 in the upper left corner to node 1, 1 diagonally down from it, it would be a distance of 2 units in this, as opposed to 1.4 units if I were able to go diagonal. But whether I use the diagonals or not, a simple mesh is the way to go for topology. And one way to think about this is that you can have channels that are really wide and you can have lots of them. So let's look at the technology we're playing with today. In a typical chip, say a 5 nanometer chip today, our wire pitch is about 40 nanometers on dense layers. Those are the lower layers. We tend not to use those for the NOC. We tend to use the upper layers for the NOC, and they're about half that density. They're about 80 nanometers on upper layers. And we can have 20 layers on these chips. So if you count per dense layer, there's about 25,000 wires per tile edge. And so even if you take the sparse layers, the less dense layers and the 20 layers, we have 250,000 wires across the edge of this chip. If I use 512 of them to send a cache line in parallel, that's 0.2% of the wires. It's a negligible fraction of the wire density on on that. In fact, on a single layer, it's like 2% of the wires. So it's not going to be a big deal. It's going to take a tiny fraction of the chip edge to stick that thing in. And one thing that we need to look at is that the latency of the wires here really matters. So the signal velocity here is about a millimeter per nanosecond. So if I'm running a clock of a couple gigahertz, it's a couple clocks to cross one tile of the NOC. And depending on what layer you're on, the repeaters have to be pretty often. On these dense layers, the repeaters are about every 20 microns. On the sparser layers, the repeaters are every 100 to 200 microns. So that's one of the reasons we use the more sparse layers. Then you only need about 5 repeaters across the NOC. And the energy is 50 femtojoules per bit millimeter. That's a lot. Going through the router is a fraction of this energy. A fraction of the energy of crossing a tile. So I think I went backwards there. That's topology. The next step of the recipe is look at routing, and I would argue here to make it simple direction order. Basically, if I'm in a mesh without diagonals, X first, then Y until I get to the destination. If I'm in a mesh with diagonals, take the diagonal first, as long as I have differences in both X and Y. And then as soon as I have a difference in only one dimension, go in that dimension until I reach the destination. This is, very simply, I can make the decision here very fast, and I'll give an example of a router that does this. I simply have to take the packet header where I have the X and Y destination, and then I've pre-computed at the source the sign of the difference of X and Y, right? So if I'm going west to east, that's a positive sign in X. If I'm going east to west, that's a negative sign in X. Similarly, south to north is a positive sign in Y, north to south is a negative sign. And these two sign bits will select for a given direction, which direction I want, for a given dimension, which direction I want to go. And then the equality comparison between the destination bits and the current location will give me the selection of diagonal X or Y. So for example, if I mismatch on both X and Y, I'm going to pick a diagonal. I will pick one of the 4 diagonals based on the 2 sign bits. If I match in Y, but I mismatch in X, I'm going to pick one of the X directions, and I'll pick that X direction based on the X sign bit. If I match in X and mismatch in Y, I pick the Y direction, and I pick the channel based on the sign bit in Y. And if I match on both, I pick the output port. So it's really simple logic. It winds up being about 6 layers of gates. So with a fan out of 4 delay of about 10 picoseconds, this is a 60 picosecond routing decision. So flow control, and we've done lots of fancy things with flow control over the years with virtual channels and lots of neat techniques to make this work well. In many ways, that's all overkill. I think the right way to do this is to use good old-fashioned 2-cycle asynchronous flow control. And I will refer back to one of my mentors, back in my Caltech days, was Ivan Sutherland. And he wrote this paper on micropipelines as it was his Turing Award lecture. It appeared in CACM in June *89. And this basically, he didn't invent this. This goes back probably to the 50s for asynchronous logic. A very simple flow control mechanism where if you are the sender, you put data on the line and toggle your request line. And so somebody actually put this data on the line over here and toggled the request up. You then hold that until you get an acknowledge. The acknowledge samples the data and allows you to change the data to put new data on the line where you can request again. And you have to hold that data on the line until you're acknowledged. Very simple flow control. There are no virtual channels, no credits. And we don't need them. Wires are plentiful. So if we need another channel, we add a physical channel. And in fact, even for the simple case I'm talking about of a multi-core CPU network, we will at least need one network for requests and a different one for replies, because otherwise, even though our direction order routing is deadlock free for one set, we could have a coupling through the client from request to reply. And if we don't have a separate reply network, we could induce deadlock that way. And then we also want to make this asynchronous. And the reason is If I were to make this synchronous and I'm dialing the clock rate of my chip, and by the way, these typical multi-cores, you'll run each core in its own clock rate, because depending on whether it's doing something urgent or not, you will run its clock and power supply up and down. So you would be having to do a synchronization at the destination anyway. But if I ran the whole network on a global clock, my bits would zip across the tile and they'd get to the register and they'd have to wait for the next clock edge. And that's wasting precious picoseconds, essentially rounding up my delay to the next clock. And then in designing the router, I will apply the KISS principle of keeping the router simple. And so here is almost to the level of gates, a super simple asynchronous router. And I'm showing one input port and one output port. And I should have actually drawn a line here down the middle of this slide. Up through this R block, the I block and the R block are the input port, and the A block is in the output port. And the way it works is simple. I have a I block, which can be as simple as a C element, although you may want to make it a little more complex, where when my request comes in, I look at the acknowledge from the port that I have been granted, if I've been granted it yet. And I use that to control a latch enable for the input latch. So originally the input latch is open. So when the data arrives, it can flow right on through, and flow through to this AND gate and stop, because the other input to the AND gate will be 0 at that point. In the meantime, I've made a request. That request will get forwarded to the routing block. And the routing block will look at that header I talked about, the X destination, Y destination, delta X sign, delta Y sign. It will compare XD and YD to XC and YC, the current X and Y. And based on those two bits, it will select diagonal X or Y. And by the way, that compare is a single rank of AND. Then once I take what comes out of that compare, I've got 2 bits. That goes into another rank of AND with those 2 bits and the sign bits that actually select the channel. Now for the West input, the possibilities for channels, it really should be, if I do X first, it really should be 5 here. The two possibilities are 3 or 5. It's either I pick the East output. Oh no, it is 4. Okay, I pick the East output. I pick the North output, the South output, or the output to the port. And so depending on which one it is, in this case, say it's the East output, I will take the fact that I have a request, and that request is for the East output, and I will send it to the arbiter. This is simply a 4-input arbiter that will select who made a request first among these 4 inputs. And typically the way we build it, the 4-bit input arbiter, is we build it as 2 2-input arbiters stacked after each other. So we'll arbitrate among these 2 and then these 2, and then feed those into another block that will flip-flop between them. And each of those arbiters is essentially an RS latch. So that's another pair of gate delays. And then if say nobody else is making a request, our request will propagate through to the grant. This grant will do 2 things. One is it will enable the data onto the wires that head out to the East port. This is a simple and/or multiplexer. So that the data wires are now on their way to the next router. And in the meantime, the request line for that next router also will toggle. And then it will send up to here. And this and/or is simply selecting the grant that I'm requesting to feed back into my acknowledge. It will acknowledge me, which then means that I have sampled this data, and the person downstream can go ahead and change it and send the next one. And even being pretty generous, counting logic delays, this is 100 picoseconds from the request in to the request out. And actually less than that from the data into the data out. So the data will get ahead of the request, which is what you want. So it's 100 picoseconds to go through this logic. And even for a 1 millimeter tile, it's a couple, a nanosecond or 2 to get across that tile for the channel. So the channel is dominating both power and latency getting across here. This just shows the propagation through here, where I'll have, the thing here is request West input goes high. So after that goes to the routing block, it makes the request West East, which is the blue line here. That goes to the arbiter, where we get the grant West to East. That's the brown line here. that then triggers the request east output, right? That's the input to output. If you count those gate delays, the C element's one gate, the routing block here is 2 levels of gates. The arbiter block is another 2 levels of gates. So 1, 2, 3, 4, 5, 6, and I'm out, and I'm counting it as 10. It's very fast. And then the back path here is once I get the grant and the acknowledge east output, the grant will gate that acknowledge back to my acknowledge, and I'll finally get the acknowledge west input, and I can send the next piece of data. For planning, if I assume that I have the diagonal, if I don't take the red and the white off here and only leave the cal colors. The router is in the northwest corner, and as I said, even if I do this, on a single thick layer and I have 512 bits, I'm using like 2% of this edge, right? So this is an exaggeration, showing it as almost a fifth of the edge. It's going to be a tiny little piece of the edge up here. And the west-east router is in this block, the north-south router is in this block. So all those wires I just showed you in the previous picture, all the ones down here actually, are really short. And even the connection from the west-east router to a north-south router, if this was, say, a north or south output, and I had to go from my R block to their A block and back again, is going to be short, because I'll put all the requests, all the R blocks and A blocks in the north part of west-east and in the west part of north-south. So they're going to be right next to each other. So everything is going to be short wires in the routers. So just to summarize the router design, there's no virtual channels here, no credits, just 2-phase ready acknowledge protocol. This gives us a minimum delay input to output. And we don't need more. Making this more complicated would only slow it down. I've looked at recent designs of NOCS, and somebody who does a really good NOC design takes 1 clock cycle to get through the router. I've seen some where it's 2 or 3, and then this is less than this is 100 picoseconds, which is maybe, depending on your clock cycle, somewhere between a fifth and a tenth of the clock cycle. There's no reason to add all that extra delay, which would double or triple or quadruple the delay across your NOC. This is sort of a 10 to 20% or less, depending on the size of your tile, increase in delay over the time of flight wires. And again, what we're trying to do here is get the NOC to be as fast as if you put dedicated wires down for the packet you're sending. So I had to go back into a little bit more history. The first use of the 2-cycle ready acknowledge protocol in a router that I'm aware of was actually this Torus routing chip that I designed in 1985. This was the paper that came out in 86 and distributed computing on it. And just to show that it was a real routing chip and not just a simulation, I had to include this scope photo. But this was the the output request toggling, and that toggling then led to the input acknowledge. The input request toggled, that led to the input acknowledge toggling after the output request had actually toggled. The input was actually driving this. For reference, this was done in 3 micron CMOS. That's micron, not nanometer. Now, the numbers on current design technologies are a little optimistic because they have scaled some kind of effective gate length. But what really matters in a technology is the wire pitch. In 3 micron technology, these were done in Lambda design rules. So Lambda was 1.5 microns, and the wire pitch for Metal 1 was 6 Lambda. So that would have been basically a 9 micron wire pitch. So 3 times the technology. The 3 nanometer technology doesn't have a 9 nanometer wire pitch. It has a 40 nanometer wire pitch. So things have not scaled quite so much. But if you took the scaling literally, you would get 1,000 times in both the X and Y dimensions from this 3 micron to today's 3 nanometer, and that's 1,000,000 X in area. So that makes some qualitative differences, the kind of things that you can design and what is optimal. The other family of routers that sort of came after this, it was some way motivated by the Torus routing chip and fixed a number of things that were wrong with the Torus routing chip, were a whole family of chips that my former PhD advisor, Charles Seitz, did with some of his later graduate students, including Nan Bowden and Wenking Su. These chips actually went on to be used in things like the Intel IPSC2 and the Intel Paragon, which was one of the biggest supercomputers in its time. And these also, I think, showed the advantage of the simple 2-cycle request acknowledge protocol. they optimized for throughput rather than latency, which was the right thing to do for an off-chip router, the wrong thing to do for a NOC. Because again, remember, an off-chip router, you're making lots of design trade-offs to optimize the use of scarce pins. In a NOC, you don't have pins and the wires aren't scarce. So some of the things that were done here to share and the deep pipeline, even though it's an asynchronous pipeline, it still adds latency compared to coming in and getting right out with almost no logic at all. And it borrowed from the Torus routing chip. The Torus routing chip, it actually doesn't show it in any of the figures I copied out of the paper here, but it used a header design where you sent the remaining distance in X and Y. And so with whichever dimension you were on, you would decrement the header. And when it got to 0, you would strip it and jump to the next dimension. That wound up adding latency because a decrement's a lot more delay. It has a delay that's proportional to the log of the number of bits compared to that simple AND of just doing a comparison. Another, going through the history of stuff technique, which is sort of being borrowed here. And in many ways, this was sort of the synchronous version of the two-cycle protocol, was the elastic buffer flow control that my former PhD student, George Miklajaniakis, came up with. And in this case, just as with the two-cycle flow control, you present your input data, and then you present what's essentially a request, but in the synchronous, delay insensitive world, we say valid. So this line goes high simply to say that the input data is valid, and the R line is ready. And so if valid and ready are high at the same time, it means I have data and you're ready to take it. The transaction is assumed to have taken place, and we capture that in the master latch. And one of the points we made here is that a typical D flip-flop has a master latch and a slave latch. By the way, we're no longer allowed to use these terms at NVIDIA. We have a new book of correct language that replaces these. I'm trying to remember what I think it's kind of the primary and secondary latch or something like that. From that, we can use both sides of the D flip-flop and hold 2 bits of information in the D flip-flop rather than just one by having this elastic buffer control logic down here. So just to summarize on the router and that brief segue in history was to point out some of the things that some of the history that this super simple router design is motivated by. It's just a simple 4 or 6-way split merge, depending on whether you have diagonals or not. R is basically a pair of AND gates, one for X and Y, followed by another set of AND gates to drive these dimension selects. A is just a couple RS latches, and then the other ones I've actually labeled what the logic symbols are. I, by the way, is the C element. The C element, for those of you who aren't familiar with asynchronous logic, is a logic gate. It's a synchronous, it's a sequential, asynchronous sequential logic gate with 2 inputs. And basically the output will go high when both inputs are high and low when both inputs are low. And when one input toggles and the other one doesn't, it waits for the other input. It is an illegal operation to have one input change and then have that input change again before the other input. So let me move now to circuits. This is the one thing I think I had right in my keynote 15 years ago. Circuits matter. We'd like to be sending our signals across the tile at 10 femtojoules per bit millimeter, not 50. And this is super important because in a lot of these systems, the communication energy dominates and the wire energy dominates the communication energy. So if I can cut my wire energy by a factor of 5, I can cut my overall energy by something close to 5. We actually talked about this a little bit back in this 2006 paper exploring on-chip NOC technologies. And this is one with James Balfour. And we basically used a simple first order repeated wire delay model. That's still what people use today. But things have changed a little bit. Back then, I think this was probably 2006, 65 nanometer technology. The wire pitch was 200 nanometers on the actually 400 on the ones you would use, the thick layers. Now that's down by a factor of 5 now. So notice scaling from 65 nanometer technology to 5 nanometer technology. You would think that would be a factor of 13. No, it's a factor of 5. Again, this is sort of the truth in advertising of the advertised numbers on technologies. And the resistance and capacitance have gone way up. The resistance ohms per millimeter there is 350 ohms. It's now 150 k ohms for the local and 18k for the global wires. The good news is we're still getting, order of a millimeter per nanosecond on these wires. This is a paper that we had in the International Solid State Circuits Conference in 2016. Let's see, what is that, 6 years ago? And the problem we were trying to solve was how to reduce the energy for sending wires across chip, and at the same time also reduce crosstalk, which is an important problem. And so I'll talk about both of those here. The way to reduce the energy is to use every electron twice, and through the great laws of physics, this actually gives you a 4x energy savings, not 2x. So the simple way to think about this is you know that if you were to just drop the power supply in half, say I had a 1 volt power supply and I started a signal with a 0.5 volt, which by the way is way more than you need. The energy is dominated by the capacitance of the wire and is CV squared energy. So cutting the voltage in half cuts the energy not in half, but in a quarter, because you're cutting both the voltage and the current in half. And so you could do that, but then you would need to actually generate a 0.5 volt supply. And that would probably have 20% overhead with it and would require another regulator, another power distribution network on your chip. So the clever thing we did in this paper was we generated a 0.5 volt supply by simply using the 1 volt supply twice. We sort of had a 0.5 volt supply from 1 volt to 0.5, then another 0.5 volt supply from 0.5 to ground. And we did this without regulators. And the reason it worked without regulators is we made sure the current draw in the upper deck and the lower deck were exactly the same. And we did this by taking the signals and switching them back and forth over the course of a millimeter route, so that we had exactly the same signals toggling on the upper deck as on the lower deck, and the capacitance was exactly the same. So the current draw was exactly the same. And so this was, I think the next picture shows the demonstration. Maybe it's a couple more. I guess I never showed the die photo for this. So we prototyped this, and in video, the way we prototype a lot of things, it's very expensive to tape out a chip, even a shuttle. So what we do is when a new GPU is going out or a new switch chip, we go and talk to the manager for that chip and find out if there's any idle area. And so in this case, there was a little corner somewhere that was unused. Back in the old days of chip design, that was unheard of. You were considered a bad chip designer if you didn't use every square millimeter of the chip area for something useful. But these days, the premium is on getting the chip out the door completely verified, so it works the first time. And very often that actually leaves a little bit of unused chip area. And so we put an experiment in there of this. And so prototyped one of these. These energies per bit millimeter are actually measured. And the rough gain is a factor of 4. That's a huge gain. The other thing that we did with this is we observed that one of the problems we were having with long routes of on-chip wires is there's a huge amount of crosstalk. And the reason is that the wire capacitance dominates energy, but a lot of this wire capacitance isn't to ground, it's to the next wire. These wires are actually, they're shown as kind of square here, but they're actually taller than they are wide. And that's because you want to make the resistance per millimeter as low as you possibly can with the higher possible density. And so you use the highest aspect ratio that you can get away with in that lithography. And so the capacitance to the adjacent wire is often higher than the capacitance to the power or ground, which actually isn't really power or ground. It's the wires on the layer above you and below you. So in this case, we ran a fabric where we had a power wire, an east data wire, a west data wire, and then a V mid wire, east data wire, west data wire, and ground wire. These are all 80 nanometer width and spacing in this particular technology. So comparable to what you get on upper layer today. And what we showed is that we essentially completely eliminated the crosstalk by doing this. And the intuitive reason for this is that when I'm having crosstalk with somebody going in my same direction, the crosstalk is huge because I have an edge and you have an edge, and they're traveling along next to each other over a long distance. And therefore, they're interacting for a long period of time. And over that long period of time, the interaction integrates up and increases. But if I have an interaction with somebody going the other way, it's, it's like two cars passing on the freeway. I interact with you for a really brief instant, and then you're gone. And over the course of my travels, I'm going to see an equal number of up and down edges simply because they have to alternate. And so essentially there's no crosstalk to these adjacent wires. It's as good as having a ground wire next to you. And then in designing these things, I'm not quite sure how that got in there. It's really important. Oh yeah, no, I remember why I put this in there. It's really important to make sure you put in the other communication primitives you need, and that includes synchronization primitives. So when we did the Simba accelerator, we didn't have a synchronization network, and it wound up for the small when we started getting the large number of PEs handling relatively small networks. At the end of every layer, we would have to do a barrier synchronization to make sure everybody was done before starting on the next layer. And that barrier synchronization being done in software, sending packets over the regular NOC, wound up being pretty slow. And so the a technique that, at least in my knowledge, goes back to when we built the Cray T3D, which we started that project in 1989, and we shipped the first one in 92. We built embedded into in that case, it was a over wires between nodes network, but you can do it in a NOC as well, a fast barrier network. And what you do is you simply build a tree of AND gates, and you have several barrier bit vectors. Every node has a register. You probably put 32 or 64 of these barrier networks together, and so you would set one bit of your network to say I've arrived at the barrier, or if you're not participating in that barrier, you set that bit of your network. And then when your neighbors arrive at that barrier, they set theirs. You've embedded this tree into your two-dimensional topology, and at every intermediate node of that tree is an AND gate, or 32 or 64 AND gates, one for every one of the virtual barrier networks. And when they get to the root of the tree, you simply turn that around and broadcast it back down so that everybody sees the value of the root, which is the value of the network. And that way, essentially, in time of flight over wires, you can have a barrier. That still means something on the order of, for a big chip, 20 or 30 nanoseconds for a barrier, but 20 or 30 nanoseconds is better than a microsecond, which is, or maybe even 5 or 10 microseconds, which is what you might get if you tried doing this in software by sending packets around. And if you want to do something fancier than a barrier, say you want to do a reduction, throw an add or whatever other associative operator you want in there, and you can get very fast summations and reductions as well. And again, for certain computations, this can remove bottlenecks. So some details for the recipe before I go on. So you're going to want separate networks for request and reply, since we don't have virtual channels. Otherwise, we'd get a request reply deadlock, because even though X and Y can't interact with dimensional rerouting, if I do X, Y, and then I somehow couple that through the receiving node from the request into the reply, where I then do X, Y, I can now create a cycle, and I don't want to do that. We also want to put separate networks for anything else our system needs. Remember, we have lots of wires. And so if I decide I want to have a premium class of service, rather than adding a virtual channel for that, remember, the reason we had virtual channels is because we wanted to share scarce pins. Pins aren't scarce anymore. We have plenty of wires. We just add a high priority network. We'll add the barrier network, we'll add collective networks, whatever we need. There's nothing worse than building a really fast network and then blowing it all at the synchronizer. The default synchronizer that we use at NVIDIA, which I refer to as a brute force synchronizer, is an asynchronous FIFO that uses basically multiple sampling of the essentially the ready bit of the valid bit coming out of the FIFO to move it from the one clock domain to the other. And today, to get acceptable synchronization failure rates, that adds 4 or 5 clock cycles of latency, and that's horrible. We have a number of, and I encourage you to go look at the async conference proceedings to see a number of these, but we have at least 2 or 3 different designs of what I call half cycle synchronizers, so that basically your packet arrives, let's just say your clock edge arrives, and a decision is made whether you're in the good window or not. And if you're in the good window, you just get sampled by the next clock edge of that node. And if you're not in the good window, you wait until the next clock edge, right? And so on average, it delays you a half a cycle to line up with the next clock edge. You don't wind up waiting 4 or 5 cycles, which is the amount of time it takes for a potential metastability to decay. And this is important because in some of these networks, you're going to be 4 or 5 cycles getting across the network. You don't want to double your network delay with a synchronizer. It's also good when you design the network to put some loggers on it, so that you have a way of essentially either, think of this as building a logic analyzer into your network. So you can, trigger on something and then basically dump the contents of the network for the next period of time until you either re-trigger or run out of storage. And this can be done on the sides. There's no added delay in the critical path, but for certain debugging tasks, it's really valuable to have your logic analyzer built in there, since you don't have the room to go and take the probes and connect it up. So now the fun part of the talk. Let me speculate a little bit about future directions. So one thing we see happening a lot is whether it's on an organic package like this Simba thing, or this is a concept we had where we actually stack several things on an interposer. These NOCs are now being extended to network on package. And this is sort of this intermediate point between a traditional network where we're really super constrained by pins, where the cost is dominated by the active optical cables, and an on-chip network where we're not constrained by pins and wires are free. And this intermediate point, I think, will yield novel solutions to a bunch of the classic problems of topology, routing, and flow control. We still will need virtual channels or the like, maybe not the whole way through the network. Maybe we only need virtual channels to traverse, the place where pins are scarce, at the edge of where we're going from one packaging domain to another. And then we'll go back to physical channels on the other side. To give you some ideas of pitches, remember we have sort of an 80 nanometer pitch per layer with 20 layers on the die. The best technology that's shipping today is hybrid bonding technology with about a 5 micron pitch. So we go from 80 nanometers to 5 microns. That's order of a factor of 100 less density, and there's only one layer of those. And that's with hybrid bonding. If you're doing more traditional solder ball bonding, even going to an interposer, those are order of 20 or 40 micron pitches, and to a package, they're order of 100 micron pitches. And so they're you're going up several orders of magnitude in wire pitch, down several orders of magnitude in density. And so optimization of wires at boundaries may make sense. I think that there's a lot of room for better circuit design. And what you'd really like to do is have lower energy wires without sacrificing latency. The simple solution here, and it may be the right solution, is just to lower the voltages at which you signal. And whether you do this by lowering the power supply voltage or having an efficient way, remember if I have a 1 volt power supply and I send a 20 millivolt pulse across this wire. Let me make it simpler. If I have a 1 volt power supply and I send a 0.5 volt pulse across this wire, if I do that by resistively dropping that power supply, I don't get the quadratic gain. I only get a linear gain. To get the quadratic gain, I have to efficiently convert, basically using L's and C's only, no R's, that 1 volt power supply down to the 0.5 volt to transmit it. Now getting 50% is better than nothing, but we'd rather get the 25% of the energy, not the 50%, and that requires efficient conversion. The other thing that I think, and people haven't really tried this, is to get faster wires. People feel very constrained by what's called the optimum repeater delay wire. So it turns out that there's an optimum repeater spacing for wires, where if you space the repeaters closer than that, you'd be dominated by the delay of the inverters. If you space the repeaters further away than that, you're dominated by the delay of the wires. For the 80 nanometer pitch wires today, that spacing is right around 100 microns. Most people don't place the repeaters that often because it's less energy efficient, and it takes a lot of area to put all those repeaters down. They're not minimum sized devices. But there's an interesting question about what is the maximum achievable signal velocity for these 80 nanometer pitch wires. I don't know the answer to that question, so I'll pose it. When I wrote one of my textbooks with John Poulton back in 1998, I wrote a little section on, and I just sort of thought of this while I was writing the book, of how to overdrive low swing RC lines. And the thought is that if I really want to get, say, 100 millivolts on the line, what I can do is I can pulse that line up to 1 volt and then back down to 100 millivolts. And the propagation across RC lines is governed by the heat equation. So it's basically a diffusive propagation. So as you move down the line, and these are spaces, at the head end of the line, 20% of the way or 25% of the way, halfway, 3/4, and at the end of the line, what you see is at the end of the line, you get a nice little rising edge here. What it doesn't really say is that compared to just driving this line normally, this edge happens about a factor of 3 faster. So this is one potential way, and this is just equalization. I'm taking a line with a certain, linear diffusive characteristic, and I'm computing the optimum waveform to drive that with to get me the fastest possible line. Then I think that also synchronizers are a real issue here, and I think there's a lot of room for research in synchronizers. This is a paper from 3 authors at NVIDIA and Berkeley that is one of the half-cycle designs I referred to. It requires that you have a plausible clock for your receive logic. This is the old-fashioned brute force synchronizer. In this case, it would be a 3 clock delay. These flops here are the ones that are basically taking your ready signal, in this case, the read point from which you derive the ready signal, and delaying it to let any metastable states decay before you use it at the far end. But down here, we don't need to do that because what we do is we stop the clock. We have a transmit clock that's pausable and a receive clock that's pausable. And basically, when you try to read the FIFO, you'll stop the clock, and then as soon as the data arrives, you start the clock again. And there's a couple other versions that don't require doing that. Another key thing I think is standardized interfaces. I think we're about to enter an era where NOCs are going to become even more important because rather than people building big monolithic SoCs, they're going to build an SoC, and then they're going to leave places for people to do their special sauce on a chiplet that would then either go down on an organic substrate or on an interposer or on top of that SoC with things like hybrid bonding. And what you want to do is make those SoCs able to get really high bandwidth interconnect into what's going on the rest of the SoC, I should say, those chiplets. And I think this is really a huge thing because today the barriers to entry for somebody to start a company to go into the semiconductor industry are huge. I guess as being part of a big company like NVIDIA, I should view this as a good thing. It keeps the number of competitors down, but as a citizen of the world, I think this is a bad thing because we'd like to have lots of really smart people with good ideas starting companies. And if the ante is you have to design the whole existing world first, the DRAM controllers, the on-chip memory system, the NOC, a couple microprocessors, a half dozen required accelerators, and then you can start to add your secret sauce. The burden is too high. If instead you can buy an SoC with all that ante already done, all you have to do is design your little accelerator for which you have a clever idea. All of a sudden, the barrier to entry of starting a semiconductor company goes from $500 million down to maybe a couple $1 million because you don't even need to be in the latest technology node to do that. And I think this will be a much more interesting place. But to do that, we need NOCs. And what I've observed a lot of people do with NOCs is they still have kind of buses in their head, and they wind up with an interface that looks a lot like AXI or something like that because that's what they did last time. And we should design an interface that looks like a NOC, right? There should be inbound and outbound. I prefer to see it as 4-cycle or 2-cycle asynchronous. But even if it's simple ready valid protocols, that's fine. You want some testing ports so that both the NOC can test your module and you can test the NOC, and then we get some reference clocking there. And there are a lot of issues here with synchronization, resilience, quality of service. But we do also want to have a broad range of bandwidth demands that can interact together, right? So we might have stuff that's 256 bytes wide for really high bandwidth interface. We might have something else that's talking a really narrow interface. You need a gearbox somewhere in there to connect those together. And by the way, I talked about a lot of this stuff, and this figure comes out of there in a DAC paper in 2013. So I'm just about at time. So let me wrap up. So I've been playing with NOCs for 21 years. I've been playing for interconnection networks longer than that. And NOCs are everywhere today. I think it's actually interconnection networks are everywhere too. Their latency and power are a major factor in system performance and efficiency. So we really need to design them well, lest the products that they're in not be competitive. And my recipe for this, I just will characterize as simple and fast. One of my philosophies in life is that there's No logic gate that's faster than the one that isn't there. And so for topology, a 2D mesh, diagonals, if you can talk your technology people into them, a two-phase request acknowledge protocol for flow control, no virtual channels, no credits. Actually, the one credit is basically that acknowledge line. And this lets you then build a simple router where, I can draw on one slide, essentially every gate in that router. And that's got a fall through delay of about 100 picoseconds, not the 3 nanoseconds of some routers that I've seen recently. They basically take 3 clock cycles to do the thing. And it's basically the thing arrives and it's a clock cycle to kind of put it into that input buffer. Then you do a clock cycle orbiting for the output virtual channel, and then another clock cycle sending it from input port to output port, and then you start traversing the wire. What you'd like to do is 100 picoseconds and you're out on the wire going to the next router. And if you need multiple networks, rather than doing it with virtual channels, just lay those networks down. We need low energy circuits to drive the wires. This is a first order concern. The vast majority of the power, 90% of the power, is in those wires. And so if we can cut that down by a factor of 4 or 5, we're cutting the overall power down by a comparable amount. So for future directions, I think there's a lot of interesting things will come out of looking at what are the packaging constraints of networks on package, network on chip hybrids, where the wires are plentiful on the chip, not across the boundaries. How do we deal with that? I think there's a lot of stuff for better circuits to drive wires, both for energy and for delay. Nobody's really looked at delay much yet. There's, I think, big opportunities to do better half-cycle synchronizers. And I think there's a really educational issue here. A lot of engineers I find are deadly afraid of synchronization failure, and they know they're not going to be fired for putting in that brute force synchronizer that introduces 5 cycles of latency. I think we should fire a few of them that do that, and that will send a different message of, let's not be so risk adverse. Let's worry about performance a little bit too. We need to have standardization of those interfaces. So I'm just about at time, but depending on whether the organizers are amenable, I'm happy to answer a few questions.
All right. Thank you very much, Bill, for an inspiring keynote. So I think there are plenty of lessons to be taken from your talk. And I also enjoyed a lot, and I'm sure the audience enjoyed a lot, the historical intertwining on this current and future things. I'd like to make 2 comments. One of them, if I were to summarize the take-home message, is 3 rules for designing future NOCs. Simple topology, simple routing, simple circuit design, right? For the simple topology, the thing that you mentioned, the mesh with the diagonals, it's actually very well justified, so to speak, theoretically, because it's about inducing small world effects on chip. Essentially, at the end of the day, this is, and I'm glad to see that this direction is what you suggest for the future. One more comment and maybe question. What were your thoughts on things beyond this, like, for instance, software management, verification of these things? Are there any interesting issues that you will suggest?
Yeah, so I think the software is a layer on top of this, and so I think it's pretty independent of the NOC. I think the NOC the software drives the requirement for the NOC, and things like the requirement for fast synchronization and the like that. I mean, a lot of the demands for fast barriers come from people writing software in this sort of bulk synchronous style, where every node sort of does its work and then stops and waits for every other node to catch up. And it's true for a lot of scientific computations, where you sort of do that synchronization twice per time step. Once, and then once while you compute your local value, and then everybody kind of does halo exchanges of values, and then once to say that the halo exchanges are done, and then everybody computes their next local value. And so I think software interacts with the NOC by driving the demand for both bandwidth and synchronization. Other than that, I don't know that there's a lot of interaction.
Okay, thank you. There are 3 questions actually online. I'm not sure if you could see the chat box.
Yeah, no, I see them here. Okay, yeah. So 2 from one person and 1 from another person. Let me take the one from Alan Baum from Esperanto first.
Okay.
Okay, as process and voltage gets smaller, the variability transistor parameters gets higher. The bundled asynchronous paradigm assumes all bits arrive at the same time, but they don't. How do you account for that? That's a really good question. So you need to do some statistical analysis here. And what works in your favor is when you look at the propagation delay of the bits across a tile, you're not dealing with the delay caused by one transistor, but with repeaters every 100 microns or so, you've got sort of 10 repeaters on every wire, and they're pretty big repeaters. And so while the variation of an individual driver can be quite small, the variation of the aggregate of the one big repeater to begin with, and then the aggregate of sort of 10 of those across the tile gives you actually a tighter statistical delay than you might think. And then what you do is, after you've characterized what that statistical delay is, you basically make sure the request is delayed by more than that, right? So you're not trying to match the delay of the data on the request. You're trying to make sure that the data always gets there faster. And you actually start out with giving the data a lead, because as soon as you get the ACK from that arbiter, your data is propagating over the next channel, whereas you still have a little bit of logic to do before the request comes out of the router. So I hope that answers Alan's question. It's actually not hard to guarantee that your that your data will get there before the request. And then, by the way, you also have what you could think of as sort of setup time margin, if you want, or negative setup time, because the latch is open at the far end, and that C element takes a little while to respond, and then there's an amplification chain, which is, by the way, part of the delay I didn't talk about in the router, to drive from the C element down into the latch. And so that gives the data even some additional margin to make sure it gets there first. Okay, so I'm going through these in reverse order. So that the previous one is, from someone who invented virtual channels, it's exciting to hear your advocacy for physical channels, as wires are cheap. You suggested multiple physical NOCs, requests and responses for protocol deadlock avoidance. Do you still believe VCs are valuable for performance, i.e. mitigating head-of-line blockage? So I would say for performance on a NOC, no. I think if you want performance on a NOC, put down wider channels or multiple channels, but not virtual channels. I think VCs have a huge use when you have a scarce bandwidth resource, when you've got to go through a bottleneck. And the example of that is pins on a chip, or going through hybrid bonds or solder ball bonds from a chiplet to an SoC. If you've got to narrow things down and you want to make sure that scarce resource is used 100% of the time, then use VCs to multiplex it, right? What VCs are for is a way of multiplexing a scarce resource so its utilization goes up. But for on-chip wires, I don't care what their utilization is. You don't need VCs. So let me go to the other question, then I can let you guys get not too far behind schedule. Okay, great talk, Bill. Thanks for your perspective. Another question came up. For accelerators, including GPUs that need high bandwidth from the NOC, from several SMs to the memory controllers, do you still believe meshes with multiple physical channels are the way to go instead of hierarchical crossbars? Short answer, yes, because what matters is the wire delay, right? And if I have a hierarchical crossbar, if I basically take essentially, all of my, SMs, have them drive into some central crossbar or a local crossbar that then drives into the central crossbar. In the worst case, I'm going to be going farther distance with the wires than the mesh with either the simple XY or the diagonal XY connections. And you want to have the minimum physical distance. That will give you the minimum latency, the minimum energy. Okay, so another question, do I have time to answer this one, or do you need to move on?
I think we're a little bit late. We can have your answer, a short answer. And actually, I use this opportunity to invite everyone to the panel that we have 3 hours from now, where Bill will participate. And then will be, 45 minutes of questions and answers. So you can hold on some of these questions for the panel too. Yeah, so please, if you could provide an answer.
Yeah, well, this is a question about topology, and I can have a quick answer, which is, simple topology routing for a mesh rather than a torus. And I think it holds true for anything, not just CPU or GPU. And again, the answer is simply because it's the shortest distance, and the shortest distance is going to give you the minimum delay and the minimum energy. In the question, he mentions the Google TPU V4, which uses a 3D torus and a 2D torus. And I think they use that because they're having one network that's connecting off chip, right? And for off chip, the torus still makes a lot of sense. Although quite frankly, things like a Dragonfly seem to be kind of winning these days for off chip. But on chip, it's a different set of things. When you have one network that has to be on chip and off chip, then I think you want to think very carefully of how to do the hybrid between the mesh on chip and something else off chip. Okay. Well, thanks a lot, everybody. It was my pleasure talking to you, and I look forward to seeing you all on the panel.
Thank you very much, Bill. I'm sure the entire audience will like to thank you, and hopefully we'll have another great talk at NOC 25. Okay, another keynote, assuming that the NOC will be alive and kicking by then. Thank you very much.
I'll
and
be
again,
alive and kicking. Okay.
It's an invitation to everyone to our panel 3 hours from now, more or less. Thank you.
Yeah. Bye.